this lesson, we're going to be talking about gases, and in the entire chapter, we're going to be talking about gases. So we've got to discuss the kinetic molecular theory, which is 4 different statements and 4 different assumptions that we're going to make whenever we talk about gases. So the first one is that gases are a collection of particles that are constantly in motion. They are constantly moving. Secondly, is that we assume that there's no attraction or repulsion between these particles. So if they collide with one another, they're not going to stick to one another. They're going to bounce off each other just like pool balls do. Okay? 3, there's a lot of space between those particles compared to their actual size. So if you were to take a gas and compress it, the volume would decrease significantly because the volume between those gas molecules is so large. So you can compress gases very easily. And finally, the speed at which those particles move, it increases when you increase temperature, which makes sense because if you're going to give gas molecules energy, they're going to start moving faster. Okay? So one term we have to talk about when we're talking about gases is pressure. Okay? Now pressure, one term that we will be talking about is atmospheric pressure. And so that's the amount of pressure resulting from the air pushing down on us. Because if you can imagine, the air above you is like a column, and it is a column which will push down on you because there's a large amount of gas above you. Now the interesting thing is if you are at a lower altitude, the pressure will be higher because there's more air above you pushing down on you. While if you're up in the mountains, the pressure will be less because there's literally less air pushing down on you. So that pressure, that pushing, results in a number of different differences that result when you're in the mountains versus when you're at sea level, which we will discuss later on. Okay? So pressure, we need to, now that we've talked about it qualitatively a little bit, right? The pressure is a force that's exerted over a specific area. So we're experiencing atmospheric pressure right now as you're watching this video. We need to give it units, of course. So units of pressure include atmospheres, kilopascals, and millimeters of mercury. All right, so 1 atmosphere equals 101.3 kilopascals, and that equals 760 millimeters of mercury. So these are the most common units for pressure for gases that you'll see in this class. So let's convert. If I give you 1,277 millimeters of mercury, and I ask how many atmospheres that is, what you need to do is you're going to write your given, that I'm going to get out of millimeters of mercury by putting it on bottom. I'm going to get into atmospheres by putting it up top. Then I know that there's 1 atmosphere for every 760 millimeters of mercury. So what I'm going to do is I'm going to divide 1,277 by 760. I want 4 significant figures in my final answer. So my final answer will be 1.680 atmospheres. And that's all there is to converting between units of pressure.
So now that I've shown you guys how to convert between different units of pressure, I wanted to really quickly explain where some of these units came from. So the one that we'll most often use is atmospheres. Now atmospheres, where that unit came from, we define 1 atmosphere as the pressure at sea level. Okay, so that ideal that when you're at 1 atmosphere, you're at sea level. If you're above sea level, like in the mountains, it's less than 1 atmosphere. And if you're below sea level, then you're above 1 atmosphere. There are some other units. So for example, millimeters of mercury. Where the heck did that term come from? Well, what actually happened was they took this glass tube, filled it with mercury, and inverted it. They flipped it upside down. And what happens is if you are at 1 atmosphere, that atmospheric pressure is going to push on this pool of mercury that you see in the diagram, causing the column of mercury to rise up to exactly 760 millimeters of mercury. So that's where that unit came from. There is another unit of pressure that I didn't previously talk about, and that's torr. Now, the easy thing is that torr is the exact same unit as millimeters of mercury. So 1 atmosphere has a pressure of 760 millimeters of mercury and 760 torr. Now, where the term torr came from is Torricelli, who was a scientist. So all of these units, and whenever you're looking at constants and everything like that throughout this class, if you see a name that's kind of weird, like Torricelli or Planck and etc., it's named after someone who did work related to that field. And so in order to honor that scientist or that mathematician, they name a unit after them, just like we name some elements after scientists as well. All right, so really quickly, just as a quick review, we spent an entire unit on gas laws last year. However, we're not, in AP chemistry, you're not required to name the gas laws. If you remember them, fantastic. And we never really do, rarely, I'm not going to say never, we rarely do calculations with these gas laws. But it is important for you to know the relationship between specific measurements that we can make for gases. So temperature and pressure. Remember, temperature is how fast molecules are moving. And so if I increase the temperature, what's going to happen is those molecules are going to collide with the sides of the container more frequently. And so as a result, when temperature increases, pressure will also increase. And so we say that they are directly related. And so this comes from Gay-Lussac's law. Okay, temperature and volume. So if you increase the temperature of a gas and it's within a container whose volume can change, because for the previous one with pressure, we assume the volume doesn't change. But if the volume could change, what happens is that since the molecules are moving faster, they're colliding with the walls of the container more, the volume itself is going to increase. So again, temperature and volume are directly related. Okay? Notice if temperature and pressure are both changing, your volume is not changing. Or if temperature and volume are changing, you're not changing the pressure. Okay, that's the assumption we're making. If all three change, then we use what's called the combined gas law, which we're not going to use in this class. The main point is for you to be able to compare, okay, if I increase the temperature, what happens to pressure? If I increase temperature, what happens to volume? And the one that we're going to use the most often is the last one, volume and pressure. So if you decrease the volume of a container, as a result, gas molecules are going to collide even more frequently with the walls of the container, causing the pressure to increase. So when volume decreases, pressure increases. That is an inverse relationship. Okay, they're inversely related, and that is Boyle's law.
Times volume equals N times R times T. N is the number of moles, R is a constant, and T is your temperature. And so we'll either call this the ideal gas law, PV equals nRT, or as a nickname, just PivNerd. Okay? So as a reminder, P is for pressure. The units for pressure need to be in atmospheres. Okay, so if you're given millimeters of mercury or you're given kilopascals, you got to make sure to actually convert that. V is your volume, and volume has to be in liters. N is your number of moles, and so that's going to be in moles. The reason why your pressure and your volume, your number of moles, and your temperature have to all be in certain units is because of your R. Your R is your gas constant, and it is 0.0821. Notice the units are atmospheres times liters over moles times Kelvin. And so that's why your pressure needs to be in atmospheres, your volume in liters, your N, your number of moles in moles, and then temperature, T, has to be in Kelvin. Okay, so just make sure, unlike your other gas laws where the only unit that you had to be concerned about was making sure that your temperature was measured in Kelvin, for these problems, all of your variables have specific units that they must be in. So just make sure you're careful with that when you're doing these problems. So let's look at an example. It tells me I have 4 moles of a gas at a pressure of 4,256 millimeters of mercury and a volume of 12 liters, and it's asking what is the temperature, all right? So I'm going to use PV equals nRT. My issue is that right now my pressure is in millimeters of mercury, so I need to convert that right now into atmospheres. So I'm going to plug that in. I'm going to put millimeters of mercury on bottom. I'm going to put atmospheres up top. For every 1 atmosphere, I have 760 millimeters of mercury. So I'm going to take 4,256 and I'm going to divide that by 760. And what I get is 5.600 atmospheres in order to maintain significant figures. Now, I've got my pressure in the units it needs to be in. My volume is already in liters, which are the units that I want. I have moles, and it's asking about temperature, so now I can plug everything in and solve for it. So I'm going to plug in the 5.600 atmospheres for my pressure. I'm going to plug in 12 liters for my volume. I'm going to plug in 4 for my number of moles. I'm going to plug in 0.0821 for my R value, and I'm solving for T. Okay? So make sure when you're doing this math, be careful. You're going to take 5.600, you're going to multiply that by 12, then you're going to divide that by 4, and you're going to divide that by 0.0821. Or you could take 4, multiply it by 0.0821, and whatever you get there, that's what you're going to divide the 5.600 times 12 by. Whichever way you want to do it, I actually divide by 4, and then I divide by 0.0821. That's what I just, in order to keep it in my calculator and keep it simple. Okay, so my temperature, remember, since my units for R are going to be atmospheres, liters, moles per mole Kelvin, that tells me my temperature that I got, which was 204, that's going to be in Kelvin. Now notice that as far as significant figures are concerned, I have one significant figure for the 4 moles, from the 4 moles. Therefore, I need to round this answer so it only has one sig fig, and so that answer would be 200 Kelvin. And that's your ideal gas law. That's all there is to it. So it's really not that bad. Now, we can take this idea and expand on it a tiny bit. And what we're going to do now is we're going to use your ideal gas law and learn how to determine the molar mass of a gas. All right, so in this problem, it asks, what's the molar mass in grams per mole of a gas if a 3.16 gram sample of gas at 0.750 atmospheres and 45 degrees Celsius occupies a volume of 2.05 liters. So this problem might seem super complex until you realize you're going to be having 2 different problems. The first problem you're going to do is you're going to be using the ideal gas law in order to solve for moles. So you're going to use your pressure, your temperature, and your volume to solve for moles. Once you know your moles, in order to get into molar mass, which by the way, the units are grams per mole or grams divided by moles, all you have to do is take your mass, which was the 3.16, divide it by the number of moles that are involved, and that'll give you your molar mass. So let's actually do the problem. So I'm going to use PV equals nRT. I have my pressure already in atmospheres. I have my volume already in liters. I'm solving for N, my number of moles. I know my R is 0.0821. And my temperature right now is in Celsius, so I need to convert that into Kelvin by simply adding 273. So I plug in all of my values. Okay? I'm going to take 0.750, multiply it by 2.05. Then I'm going to divide whatever I get for that product by 0.0821, and then I'm going to divide that by 318. And what you get is your number of moles, which is 0.05889 moles. Now that I have my number of moles and I have my mass, you can determine your molar mass. All you have to do is take your mass, 3.16, divide it by 0.05889. That will give me grams per mole. And so what I end up getting for my molar mass is 53.7 grams per mole once I take into account significant figures. Okay, so the only thing that I've added to this problem, the only reason why this is slightly different from just an ideal gas problem, is the fact that I'm now asking you to take your moles and apply it specifically in order to determine your molar mass. And in order to do that, all you have to do is take your mass, divide by the moles that you calculated, and there's your molar mass.
So in addition to using the ideal gas law in order to determine molar mass, we can also use ideal gas law and density in order to determine the molar mass. So if we look at this question, it says, what is the molar mass of a gas with a density of 3.50 grams per liter at a temperature of 345 Kelvin and a pressure of 0.950 atmospheres? So the hardest part about this problem, ultimately, I'm trying to get into grams per mole, which is my molar mass. And if you notice here, I tell you the density, 3.50 grams per liter. And at first you might be freaking out about those units, but all that is telling you is actually that you have 3.50 grams in 1 liter. So 3.50 grams of that gas has a volume of 1 liter. So what I'm going to do is I'm going to use my ideal gas law, PV equals nRT, and I'm going to assume that the volume I'm using is 1 liter. And I'm going to plug in all of the values that I know in order to solve for moles. Okay? So to do that, I know my pressure is 0.950. I know my volume now is 1 liter. Okay? I'm going to be solving for N. I know my R is 0.0821, and I know my temperature is 345 Kelvin. So now I can solve for my number of moles, which is 0.0335 moles. Now another way of saying that is that I have 0.0335 moles in 1 liter, right? Because my volume is 1 liter. Or I could say that's 0.0335 moles per liter. So if you notice, I have 3.50 grams per liter, and I have 0.0335 moles per liter. So if you think about it, all you need to do to get into grams per mole, which is what I'm trying to do, get into molar mass, is I need to divide 3.50 by 0.0335 moles. Notice the liters will cancel and my final units will just be grams per mole. And so the answer I get for my molar mass here is 104.35 grams per mole. So you can use the ideal gas law in order to determine molar mass if you're given the mass or if you're given the density. Another way I'm going to redo this problem at the very last step of this problem. So instead of just dividing the density by the moles per liter, which is what you calculated using your ideal gas law, another thing you can do is you can use those moles per liter as a conversion factor. So you know your density is 3.50 grams per liter. I'm going to multiply that by, well, I want to get into grams per mole. So I want to keep my grams, so I'm not going to get rid of that. I'm not going to put that anywhere, but I want to get rid of liters. So I'm going to put my liters up top, and I want to get into grams per mole. So I'm going to put moles on bottom. Now I can use the mole per liter that you just calculated using your ideal gas law. So I know that there are 0.0335 moles for every 1 liter. And so you get the same answer because you're doing the same process of dividing. Some people just like being able to see the stoichiometry of this a little bit more clearly than just blindly dividing. I did want to add 2 things. First of all, my answer shouldn't have been 104.35 like it was before. I didn't round to the correct number of sig figs. I need 3 sig figs, so my answer is going to be 104 grams per mole. The other thing I wanted to note, I had said in the previous slide that you're going to set your volume equal to 1 and then you're going to solve for moles. Well, a lot of students last year said, well, what if I set my moles equal to 1 and I solve for liters? And that works perfectly fine as well. You'll get a value for liters that you'll put up top, and then your value for moles would be 1, and it ends up giving you the exact same answer. So you can do it either way. But the moral of the story is if you have 2 units or 2 measurements that you don't know in your ideal gas law, setting one of them equal to 1 and solving for the other one, and then your units now, let's say you're solving for moles like I did, your units are not just moles, but it'll be moles per 1 liter. Okay?
So in this video, we're going to go over Dalton's law of partial pressures, and actually we're going to be able to apply it to the concept of collecting a gas over water, which is a lab that you guys are going to be doing in class. So Dalton's law of partial pressures is actually awesome because what it tells you is that the total pressure that's exerted on a system, that equals the sum of all of the individual pressures that gases exert. So for example, if you have in the atmosphere oxygen, nitrogen, helium, all the different gases, they do not interact with each other, which we saw when we're talking about ideal gases. They're not going to be attracted to each other. So instead, all of their individual pressures simply add up together to give you one total pressure. So that makes a really easy problem for us. So let's look at an example. It tells you air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen at 101.30 kilopascals of total pressure if the partial pressure of nitrogen, carbon dioxide, and other gases is 71.10, 0.040, and 0.94 kPa respectively? Well, I know my total pressure is 101.30, and I know the partial pressure of all the other guys except for oxygen, so I'm going to add up all of their pressures plus the partial pressure of oxygen. So all I have to do to figure out the partial pressure of oxygen is take the total pressure and subtract from it the partial pressure of each of the other gases, and that gives me a partial pressure of 21.22 kilopascals.
So to tag on to Dalton's law of partial pressures, which allows us to add the total partial pressures
all of the partial pressures of gases that are present in a container or in a situation, and that would give us our total pressure. We can also use mole fraction. So the first thing I've got to do is explain what a mole fraction is. So all a mole fraction is simply a fraction of the mole that you are concerned about. So for example, if I have moles of A divided by the total number of moles. So for example, if I had 2 moles of A and 4 moles of B, then my mole fraction would be 2 divided by 6, because I have 2 moles of A and 4 moles of B. That would be my mole fraction. So it would be 1/3, and you could actually get a decimal for it. So it's that simple. So the way that you can use your mole fraction is that your partial pressure, so let's say, for example, your partial pressure of A is going to be the mole fraction of A, so the number of moles of A divided by the total number of moles, multiplied by the total pressure. Okay? And so this is useful because if you know the relative number of moles, you can, and you know the total pressure, you can determine the partial pressure of each of the substances that's in a solution of gases or that's in your container. So let's look at an example. It says if a steel container holds 3.50 moles of hydrogen gas and 3.5 moles of helium gas and the total pressure is 4 atmospheres, what is the partial pressure of each of these gases? So if I want to determine the mole fraction of hydrogen first, what I would do is I would take the number of moles of hydrogen, which is 3.50, and divide that by the total number of moles, which would be 7.00 moles. Okay, so that's the mole fraction of hydrogen. And to determine the partial pressure of hydrogen, I would then just multiply by the total pressure, which is 4.00 atmospheres. And so the answer you get for this is 2.00 atmospheres. Now it asks for the partial pressure of each of the gases. Well, the cool thing is you happen to, it's a coincidence that in this problem you have equal moles of hydrogen gas and helium gas. So the partial pressure of each of them are going to be equal. So 2.00 atmospheres for hydrogen gas and 2.00 atmospheres for helium gas. Now notice the partial pressures, based on Dalton's law of partial pressures, the partial pressures of these two gases are going to add together to give you the total pressure. So 2.00 plus 2.00 gives you 4.00 atmospheres. So if I am for some reason collecting a gas over water, and you're going to be doing this with lighters and releasing gas, you're going to be allowing the gas to be released right over water and collecting the gas in a graduated cylinder. Well, the partial pressure of the gas that you're releasing, plus the partial pressure of water, that equals your total pressure. So that's just Dalton's law of partial pressures. So let's look at an example. Okay, when magnesium reacts with hydrochloric acid, a volume of 0.355 liters of hydrogen gas is collected over water at 26 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. If the total pressure is 7.52 millimeters of mercury, how many moles of hydrogen were collected? Okay, so imagine what you're doing is you're allowing this reaction to occur. It's occurring right over, the gas is being produced right over water, simply sometimes for safety purposes or whatever it may be. The only issue with collecting it over water is the fact that water itself is going to have a pressure. Well, that's not really an issue because based on Dalton's law of partial pressures, I know that the total pressure equals the partial pressure of the hydrogen gas plus the partial pressure of water. Well, I know the total pressure in this case is 752, and I know that the partial pressure of water is 25. And so that tells me that the partial pressure of hydrogen gas is just going to be 727 millimeters of mercury. So that's the only new concept in this entire lesson, is the idea that the two partial pressures add up to give you a total pressure. Now, it's asking me how many moles of hydrogen gas were collected. Well, I have the partial pressure of hydrogen gas, or just the pressure of hydrogen gas. I have the volume. I have the temperature. I can use my ideal gas law. But in order to use my ideal gas law, I need to get into millimeters. I need to get out of millimeters of mercury and into atmosphere. So I'm going to put millimeters of mercury on bottom, atmospheres up top. 1 atmosphere is 760 millimeters of mercury. So I know that my partial pressure of hydrogen gas is 0.95658 atmospheres. Now I can plug that in to my PV equals nRT, my ideal gas law. My pressure is 0.9568. I know my volume is 0.355. That equals, well, I'm solving for my number of moles, times my R, times my temperature. Remember, temperature has to be in Kelvin, so I'm going to add 26 degrees Celsius plus 273, and that gives me 299. So when I solve for my number of moles, I get 0.0138 moles. Okay, so all of these ideas that we've been coming up with, that we've been discussing, start with the ideal gas law, and then they're just little branches off from it. So for example, figuring out the molar mass that we did 2 videos ago, right? Figure out the moles, take the mass divided by moles, there's your molar mass. Using it in stoichiometry problems, figure out the number of moles based on stoichiometry, then plug that value into your ideal gas law, your PV equals nRT. And then in this case, if I'm collecting a gas over water, knowing that the partial pressure of the gas is simply going to be the total pressure minus the partial pressure of water, then plugging in your pressure into your ideal gas law. So all of these different ideas are coming from and are using your ideal gas law, or PV equals nRT.